Okay, picture this. You've got a colossal steel behemoth, a modern cargo ship weighing hundreds of thousands of tons sliding into a port. It looks incredibly graceful, right? Almost effortless. But beneath the surface, there is a massive, high-stakes war of physics going on. So how exactly do you bring a multi-million-ton vessel to a dead stop against a totally stationary object without completely obliterating the dock or, the ship itself? Welcome to This Explainer. Today, we are unlocking the hidden secrets of marine engineering. We're going on this epic spatial journey together, starting way down deep beneath the crushing weight of the seabed, traveling up through the corrosive water column, and making it all the way to the brutal impact zone right there on the surface deck. It's a fascinating world where structural design meets raw, untamed oceanic power. To make sense of all this, we'll follow a pretty straightforward blueprint. First, we'll tackle the hostile marine environment. Then we'll look at anchoring into the seabed. After that, we'll cover building the concrete pier. And finally, bracing for those massive ship impacts. Let's get into it. Section 1. The hostile marine environment. The invisible chemical warfare. Even before we start building, we are facing this invisible chemical war. The ocean isn't just waves and tides, right? Salt water is relentlessly eating away at our materials 24/7. Now, you might think, hey, the ocean is sulfates. We should totally use sulfate-resisting cement. Well, actually, scratch that. For reinforced concrete, that is literally a terrible idea. Here's why. Sulfate-resisting cement intentionally reduces a specific compound called tricalcium aluminate. But in a marine environment, tricalcium aluminate is actually your best friend because it binds to the highly corrosive chloride ions in the salt water. If you use sulfate-resisting cement, those chlorides just slip right past the concrete and rapidly eat away at the inner steel reinforcement. So counterintuitively, standard Portland cement is actually far superior here. Section 2. Anchoring into the seabed, the foundation. All right, so we've got the right chemistry. Now we actually need to secure this colossal structure deep into the ocean floor. Marine piles have to be driven really, really deep past the existing seabed. You might assume that hitting shallow, solid bedrock right away is the dream scenario, right? But for an open berth pier, it's actually super dangerous. Think of the pier like a giant lever. When a massive vessel pushes against it horizontally, if your bedrock is too shallow, your piles just don't go deep enough into the soil to create a long enough lever arm. You desperately need that deep soil cover to provide enough lateral resistance so the whole pier doesn't just snap and tip right over. And engineers don't just use any shape for these supports. They specifically choose circular tubular piles over square box sections or H-piles. Why? Because the ocean is totally chaotic. Forces are coming at you from every possible direction. Circular piles possess incredibly high column buckling strength, which is absolutely crucial since these structures sit so high above the seabed. Plus, they have vastly superior energy-absorbing capabilities. They are just perfectly geometrically suited to take on the multidirectional, punishing forces of the sea. But here is perhaps the absolute most brilliant trick of the whole foundation. These giant steel tubes, they aren't capped at the bottom. They are driven into the seabed completely open-ended. As massive hammers pound the pile downward, the earth rushes up inside the tube. Eventually, the friction between the steel and that internal soil gets so intense, and the inertial forces from the hammering become so great, that the soil inside literally locks together. It forms this rock-hard soil plug. The pile essentially swallows the earth and turns the seabed itself into a reinforced tip to drive down even deeper. It's just an elegant, highly effective piece of physics. Section 3. Building the concrete pier, the core structure. Moving up into the water column, we have to fill those steel piles with reinforced concrete to give them their real strength. But there's a literal internal battle happening here. As concrete cures, it does something called radial shrinkage. It actually shrinks and pulls away from the steel casing. If that bond breaks, the massive crushing loads from the deck above won't transfer properly down into the piles. So, to outsmart this, engineers do one of two things. They either weld shear keys, which are basically metal teeth, inside the steel tube for the concrete to grip onto, or they mix special expanding agents into the concrete so it swells up tight against the casing, permanently locking it in place. Oh, and pouring concrete underwater? That presents another really quirky challenge. Engineers use these long funnels called tremie pipes to place fresh concrete deep down underwater. But if they feed that concrete in too fast, a giant air bubble can get trapped inside the pipe, totally ruining the pour. The solution? Wonderfully simple. They just drop a long ventilation hose straight down the middle of the hopper to let that trapped air safely escape. It's crazy how sometimes the most complex engineering feats rely on the simplest physical solutions, right? Section 4. Bracing for ship impacts. The surface deck. When you finally break the surface of the water, you'll often spot these independent structures near the pier called dolphins. And just to be super clear, we are talking about highly engineered concrete and steel marine structures here, not the incredibly smart marine mammals. Dolphins are absolutely vital for mooring or berthing ships. They can either be built as massive, heavily rigid systems resting on multiple angled piles, or as flexible systems using a single pile that bends and sways to actually absorb the impact. To really grasp the delicate balancing act happening up at the deck level, we have to map out the forces. There's a direct mathematical relationship between the vertical load, like those incredibly heavy cranes or stacked cargo on the deck, and the horizontal capacity, which is basically the pier's ability to resist a ship pushing against it. Through simple trust action, we uncover a terrifying engineering reality. When the vertical loads on the pier are really high, the lateral resistance actually shrinks. Engineers have to calculate this perfectly. Otherwise, the pier could literally collapse horizontally under the weight of its own vertical cargo the second a ship bumps into it. So how do we soften that inevitable bump? Well, we use fenders. But not all fenders are created equal. Surface protecting fenders simply take the massive high reaction force of the ship and transfer it directly into a solid, rigid berthing structure. They basically just force the ship to stop. But for more flexible, open berth structures, engineers go with energy-absorbing fenders. These are specifically designed to take the brunt of the kinetic hit. They squish, they deform, and they transmit a much lower, much safer impact force to the actual pier structure. Now, digging just a little bit deeper into fender physics, you have to choose between stiff and soft materials. For the actual berthing phase, when that colossal ship first slams into the pier, you absolutely want stiff fenders. Even if a stiff and a soft fender deflect by the exact same distance, the stiff one is going to absorb significantly more kinetic energy during that deformation. However, once the ship is safely parked and just mooring, gently bobbing with the waves, you've got to switch over to soft fenders. Soft fenders keep the tension on those big mooring ropes nice and low, ensuring they don't snap as the ship rocks back and forth. And let's talk about what these are actually made of, because the evolution in materials here is just incredible. Back in the day, timber fenders were the absolute standard. But honestly, they're relatively weak, they rot easily, their energy absorption is terrible, and environmentally they're a catastrophe because you have to harvest all these tropical hardwoods. Today, modern ports have completely shifted to high-tech recycled plastics and specialized rubber fenders. Rubber, specifically, is a real game changer. It offers super high abrasive resistance, total immunity to biological marine attacks, and incredible energy absorption capacities, all while being vastly more eco-friendly. But check out this tiny, incredibly easy-to-miss detail that could literally bring this entire multi-million-dollar system crashing down. You could have the absolute best rubber fender in the world, but if you attach it to the pier with standard single-lock nuts, it's going to fall right off. The relentless microscopic vibration from the waves, the tides, and those minor ship bumps will literally unthread the bolts over time. In marine engineering, using double-lock nuts is absolutely essential. It is a tiny, almost invisible physical intervention that completely defeats the massive, constant vibrational energy of the ocean. Ultimately, this whole thing comes down to the core physics equation driving the system. Pay close attention to the velocity squared part of the math. Even if a 100,000-ton ship is moving at a total snail's pace, that sheer mass combined with squared velocity creates absolutely staggering kinetic energy. But there's another crucial factor here, the angle of approach. If a ship approaches perfectly tangential, basically sliding right alongside the pier, the energy absorbed by the fender is massive. But if they approach at a slightly more normal angle, the energy absorbed by the structural system actually drops significantly. The harbor pilot's steering angle literally dictates the physics of the impact. From the unseen chemical combat of salt and cement, to deep soil plugs swallowing the earth, all the way up to the intense mathematics of kinetic energy absorption on the deck, what looks like just a boring, simple concrete slab is actually a battle-tested marvel of science. So the next time you see a massive ship slide effortlessly into port, I leave you with this question. Will you just see a boat parking? Or will you see the hidden, invisible physics keeping our entire global supply chain afloat? Thanks for joining me on this explainer, and keep looking beneath the surface.